Good morning, everyone. It's my pleasure to presenting our work Toppings, a CPU-assisted rank-aware adapter serving system for large language model inference. And my name is Suyi, and I'm a PhD student from HKUST. And in this talk, I will introduce the background of generative LLM model serving, discuss the challenges in multi-tenant LoRa serving, and present our proposed solutions, Toppings, along with the evaluation results. So let's start by looking at the background of LLM serving. So with the recent advancement of LLMs in different scenarios, serving this model efficiently has become increasingly important. So given a user prompt, a typical LLM serving system workflow consists of two phases, prefill and decoding. In the prefill phase, the system processes the input prompt and generates the key value caches. This is followed by iterative decoding phases, where the LLM generates output tokens one by one based on the previous context and the cached key values. The key value tensors of the new tokens will be appended to the existing cache. So to enhance the performance of LLMs for domain-specific tasks, a technique called low-rank adaptation, or LoRA, has been proposed. The idea is to freeze the base LLM's weights and inject LoRa adapters to modify the intermediate computation results of LLM inference. So specifically, LoRa introduced two low-rank metrics A and B, and to adapt an original weight matrix W in the LLM. So given an input matrix X, LoRa changes the original computation results XW to XW plus AB. The approach of using LoRa is highly parameter efficient, as it significantly reduces the number of trainable parameters compared to fine-tuning the entire model. This is because the rank of the LoRa adapters, which is R, is significantly smaller than the hidden dimension size of W. Now let's consider the scenario of multi-tenant adapter serving, where a service provider needs to serve multiple adapted LLMs to users. And this is a practical scenario that has received interest from both industry and academia. So one straightforward approach to serve multiple LoRa's is to merge each LoRa adapter into a base LLM. While this incurs no additional inference overhead, it has limited scalability. This is because the base model needs to be duplicated for each adapter, which will quickly draw GPU memory as the number of adapters grows. An alternative is to multiplex one base LLM to serve multiple adapters. This is done by computing the LoRa adaptation XAB for each request in a batch and adding the result back to the XW. Thanks to the low rank property, this computation of XAB is lightweight, usually in the order of 1 gigaflops. So as multiple LoRa adapters can share the single base model, this approach is very GPU memory efficient. And to serve online requests to LLM models, a common approach is continuous batching, which is specially designed for the LLM's autoregressive generation process. So continuous batching operates at the iteration level, where the completed requests are immediately removed from the running batch after each iteration, and the new requests can join the running batch in just one iteration without waiting for the entire running batch to complete. Therefore, continuous batching can significantly improve the token throughput while minimizing the request queuing delays. Despite the effectiveness of LLM multiplexing and continuous batching, two key challenges arise in the multi-tenant LoRa serving. So the first is highly cumulative adapter loading overhead. So in practice, LoRa adapters are normally stored in the host memory and loaded onto GPUs on demand. While pre-caching LoRa adapters onto GPU can eliminate the loading overhead, it is infeasible as it would quickly exhaust the limited GPU memory. And loading an adapter is a time-consuming operation that can take up to tens of milliseconds, depending on the adapter size. Worse, this adapter loading overhead can accumulate as new requests keep arriving under the continuous batching scheme. So as shown in the left figure, the decoding phase is often preempted to load adapters and perform prompt processing when new requests arrive. This can lead to cumulative delays in serving a request. In the right figure, we show the proportion of the cumulative overhead, which increases as the request load increase. A second challenge stems from the heterogeneous nature of LoRa adapters, where adapters may have different ranks, which leads to variations in their computation time. So when batching these adapters together, existing solutions like padding smaller ranks to the highest one or using specialized kernels resulting in serving performance variations. We measure the decoding latency of batch serving heterogeneous LoRa's with various batch configurations. So as shown in the figure, with the same batch size, the rank heterogeneity can increase the batch decoding latency by up to 28%. So this highlights the need for a request scheduling algorithm that considers the impacts of rank heterogeneity on the serving performance. So while previous work have advanced the designs to improve the LoRa adapter serving efficiency, little attention has paid to the previously mentioned challenges. So Punica and LLM, for example, on-demand load adapters from host memory to GPU memory, which will suffer from the pre-mentioned cumulative loading overhead. And the LoRa takes a different approach by preloading adapters into GPU memory, but this can lead to out-of-memory issues when the number of adapters is large. So moreover, these works adopt suboptimal and rank-agnostic scheduling strategies. For instance, Punica uses a first-fit algorithm to consolidate GPU usage, while DLoRa employ reactive request migration for load balance, and neither of them taking into account the performance variability caused by the heterogeneous ranks. So next, let's see how Toppings work it out. So Topping addressed the challenges in multi-LoRa serving with two designs, a CPU-assisted LoRa computation and a rank-aware request scheduling. So here is the system architecture of Toppings. So new requests arrive at our rank-aware scheduler, which routes the request to inference servers. And following the continuous batching strategy, the LLM Inference server processes the request and provides generative inference service using the corresponding LoRa adapters, while the LoRa adaptation LoRa computation can be executed on either the GPU or the CPU. So to address the adapter loading overhead, Toppings propose a design of CPU-assisted LoRa serving, which offloads the lightweight LoRa computation to CPUs to early start the LoRa computation while loading adapters onto GPU at the same time. However, CPU-assisted LoRa computation introduces new challenges. First, we need to ensure layer-wise synchronization between different devices to maintain data correctness. Second, we should minimize the invocation overhead of the CPU LoRa, such as inter-process data transfer. And third, naively computing LoRa on CPUs is slow due to its limited parallelization capability. So to tackle the first synchronization challenge, we design a customized kernel that eliminates the need for explicit synchronization on GPUs. This operator ensures that the CPU computation happens at the right time without blocking the GPU. For the second challenge, we leverage the shared memory to enable fast zero-copy communication between CPU processes. As shown in the left diagram, shared memory-based communication significantly outperforms the message-based inter-process communication, which is commonly employed in LLM frameworks. So for the challenge of limited parallelism on the CPU, we optimize the CPU LoRa computation by profiling the performance of a single CPU core and employing multiple isolated processes for parallel execution. So as shown in the right diagram, compared to the PyTorch native multi-threading module, our approach can achieve 1.4 times speed up when using 16 CPUs for the same workload. And on the scheduling front, Toppings incorporate a rank-aware strategy to mitigate the performance variations caused by heterogeneous adapters. We start by profiling the performance of LoRa computation kernels under different rank configurations. Based on the profiling, we build a performance model that can predict the computation time given the adapter rank and batch size. So as shown in the figure, our linear performance model can accurately fit the prefilled data. And then when a new request arrives, Toppings first identifies the candidate servers, and then it computes a cost score for each candidate based on the performance model and the server's current load. The cost score basically measures the impact of the new request on the performance of server's ongoing request. And the request is then scheduled to the server with the minimum cost score. And this rank-aware scheduling allows Toppings to make informed decisions and improve overall serving performance. And next, let's see the evaluation. So we evaluate Toppings on the Llama 2 models with A100 GPUs. We measure the key performance metrics such as the time to generate the first token, the time per token in decoding, and the end-to-end request latency. We compare Toppings with several state-of-the-art baselines, including an ideal but impractical method where all required LoRa adapters are pre-cached in unlimited GPU memory. Therefore, for the cached baseline, it has no adapter loading overhead and achieving the performance upper bound. We use scaled production and synthetic workloads in our evaluation. A production trace is scaled from the Microsoft Azure function trace, which is widely used to evaluate model serving systems. And we regard each function in the trace as one adapter, where the adapters have varying probabilities of being invoked. So we plot the distribution of probability in the figure. And on the synthetic workloads, Toppings significantly outperforms the baselines thanks to the elimination of adapter loading overhead, achieving consistent advantages with different LoRa ranks and request traffic loads. And on the scaled production workload, we evaluate the performance of each baseline with an increasing number of LoRa's served in an inference server. So the inference server receives the aggregated request traffic from all the adapter hosts. So with more LoRa adapters, the server will receive higher request loads, and each new request is more likely to invoke new LoRa adapters that need to be loaded onto GPU on demand. So therefore, a large number of LoRa's manifest high cumulative loading overhead. And we can see that Toppings achieves more advantages when the number of LoRa adapters in the server is larger. And when we try to deploy 512 adapters in a server, the DLoRa will cause a GPU OOM. And we also evaluate the performance of Toppings scheduler against the baselines like DLoRa's load balancer and Punica's first phase strategy. So under a production workload trace, Toppings achieve a much higher SIO certification rate, confirming the effectiveness of our rank-aware scheduling approach. So let me do a quick summary. Toppings is a novel serving system that enables efficient multi-tenant LoRa serving, and it addresses two key challenges: the cumulative LoRa loading overhead and the performance heterogeneity of adapters. And thanks for your attention. I'm happy to take any questions you may have.